there are not too many reactions that normal ethers undergo. Right? And by normal ethers, we're talking just ROR, like that. Or maybe if it's in a normal, 5-membered, 6-membered ring. I like to call those normal, regular ethers. The one thing that they do that's somewhat useful to us is they can be cleaved by strong acids. That's not so useful to you if your solvent is an ether and you got some strong acid in there. You're going to have side products all over the place. But sometimes it is useful to us, especially in protection, as we'll see in the next chapter. But if I react really any ether with strong acid, we will have broken one of the OC bonds. So to figure out which one gets broken, we have to look at the mechanism. And if we're talking about acid here, the first thing we'll do is protonate the oxygen, right? Just like we've tended to do before. If our choices for the carbons here are like this one, where it's secondary and primary, then the less hindered carbon, the one that has fewer substituents on it, is more available for attack. So the nucleophile, which it's the conjugate base of the acid, that comes in and kicks out the other group by an SN2 reaction if we have just primary and secondary carbons in there. So the nucleophile ended up on the, like we see here, the nucleophile ended up on the less substituted carbon, right, the primary one. But if I have a tertiary benzylic or allylic group to it, the reaction will go first order. So our selectivity will change. So let me make benzyl. Let's do benzyl methyl ether, CH2. Benzyl, so benzene and CH2 on one side, methyl on the other side. So here is I have a primary carbon on one side. This is not a secondary carbon, this is a benzyl, because that carbon is next to a benzene ring, and that's important. So just like usual, first thing we'll do is protonate the oxygen. Benzene ring, CH2, OH, O plus, CH3. Now, what can happen is, as long as we have some sort of stabilized carbon there, the leaving group can leave on its own. That's a first order process, where what we'll get, and the reason this can happen is because what we get, if the leaving group leaves that way, we end up with a benzyl carbocation, where the plus is on the carbon next to the benzene ring. This is resonance stabilize. Right? This double bond can come out here, so this plus charge will be shared with the ortho and para positions in that ring. So it's a very stable carbocation. Right? The other product is just methanol. Then we get bromine, or whatever the conjugate base of that acid was, and attacking. So this was first order. This was an SN1 reaction, where first the leaving group leaves, right? And that only works if I have a stabilized carbocation like this one, right? It has to be tertiary, allylic, or benzylic. So as long as I get that resonance stabilized carbocation, then the leaving group can leave on its own, although that's still typically slow. Bromine can attack it that way and give us the opposite regiochemistry, where normally if I just had a primary and a secondary, in that case the bromine would have headed for the primary one quite a bit. So if there's no way to have any resonance-stabilized carbocations, then nucleophile will just attack the less hindered carbon. Okay? If I have a resonance-stabilized carbocation, tertiary allylic or benzylic, then that will be the one where the nucleophile attacks. Okay? I will not ask any questions about the next section, the Claisen rearrangement, but it's a very interesting pericyclic reaction. It's related to the Diels-Alder reaction. So read up on that. It's a really neat mechanism. It's useful for making a very specific type of alkylated benzene, but it's not general enough for us to worry too much about.